today we start with the absorption spectrum of semiconductors. Before I begin with the lecture, let me recall the quiz that I had given in an earlier class. I have already, most of you have done it rightly, but just to show the correct answer, the spontaneous emission spectrum of a particular semiconductor is given by. So, an expression is given, RSP of nu is equal to K0 x to the power half minus x, where K0 is a constant and x is given. Obtain an expression for the wavelength at which peak emission would occur. So, the answer is, while writing the answer, by mistake I wrote K0 as D, but that is the K0 which I had given in the question. So, this was by mistake I wrote it as D, but it is a constant. So, d RSP by d nu, you can split like this instead of trying to have a complex derivation there. If you split, the advantage is you first differentiate with respect to x and then you differentiate x with respect to nu, put that equal to 0 and you get x p is equal to, and then since x p is given by this expression here, we have h nu p is equal to E g plus 2 k T and lambda p is equal to C by nu p equal to h c by E g plus 2 k T. As I have seen, most of you have done it correctly. In the last class we saw about the gain and amplification by stimulated emission and the condition for amplification by stimulated emission and the laser amplifier. If we recall the same expression, our objective, as I said, was to find out if a beam of light is entering a semiconductor of I in intensity, then what is the output I out. So, this is the semiconductor, and we have got an expression that I out is equal to I in into e to the power gamma into L. If L is the length of the semiconductor, then so this is Z equal to 0 and Z equal to L, e to the power gamma n. And we had said that gamma, if it is greater than 0, it implies amplification, and gamma less than 0 implies attenuation. So, if you were to plot the intensity here versus length, so in the z direction, then if I 0 is the intensity here, that is I in is the intensity at z equal to 0, then for gamma equal to gamma greater than 0, the intensity will build up exponentially. So, up to z, so z equal to L, and after that of course outside it is. So, if I were to plot the intensity versus z, we would get an expression, get a curve like this. This is for gamma greater than 0. For gamma less than 0, it will exponentially drop down here, and then so this is for gamma less than 0, that is attenuation. We know also that gamma is a function of frequency. Gamma is identically a function of frequency. Therefore, the absorption spectrum or gain spectrum refers to dependence of gamma on nu, and we have seen that the gain spectrum, so if you plot gain versus nu, it approximately behaves something like this. So, this is gamma of nu gain. So, this is the gain profile. So, today we will see how would the absorption spectrum be, and there are many more processes, because this gain that we have calculated is gain due to stimulated emission. So, stimulated emission taking place in the presence of an incoming photon, and therefore, we have worked out that this is the expression, this is the spectrum, gain spectrum of a semiconductor amplifier, semiconductor laser amplifier. So, we will see how would the loss spectrum look like. So, recall that we have expression for gamma, which is C by n whole square 8 pi nu square 1 over tau r 2 m r to the power 3 by 2. There was 1 over pi h squared also. So, let me write it here, because this is part of the density of states, and then h nu minus E g to the power half. This was the expression that we have for gain coefficient into f g of nu, the Fermi inversion factor, f g of nu. So, if f g of nu, we first started with the 0 k experiment, thought experiment, where f g of nu was either +1 or -1, and we obtained the gain profile, and then we took a finite value and saw that the gain profile looks like this. If f g of nu were negative, so if f g of nu is less than 0, gamma is negative. Gamma is negative means we have an expression where it is E into minus gamma into L. So, if f g of nu equal to 0, then gamma is equal to minus C by n square. I will write the same expression again. Maybe I can club some of these here. So, C by n square, and there is a pi here and there is a pi here. So, pi square, and h cross square has h square divided by 2 pi the whole square. So, 4 pi square. So, h cross square is equal to h square by 4 pi square. So, this pi square cancels with these two, and 4 cancels with 2 here, 8 to give you 2, and h nu I am taking together. So, I have 2 tau r into, if I make a mistake, please point out, 2 twice m r to the power 3 by 2 into h nu minus E g divided by to the power half and h nu whole square into this quantity is negative now. So, I have taken the negative sign here, and I write this as f 0 of nu, where f 0 of nu is mod of f g of nu. Sign I have kept here, and then I want to call this as equal to alpha a minus this quantity equal to minus alpha a, or alpha a is equal to C by n square whole square. Let me write again, into twice tau r 2 m r to the power 3 by 2 into f 0 of nu. I am writing f 0 of nu into, to indicate that this is a positive number, f 0 of nu is basically mod f g of nu into h nu minus E g to the power half divided by h nu whole square. So, is the attenuation coefficient. If I plot the frequency dependence of this attenuation coefficient, I will see the attenuation spectrum. So, how would this look like? So, alpha A is basically minus gamma. So, alpha is a positive number, is the attenuation coefficient. If you see again that of course, there is a small frequency dependence here f0 of nu. What have we missed? We have not missed it. There is a frequency dependence here f0 of nu. Otherwise, it primarily depends on h nu minus E g to the power half and h nu whole square. So, if I plot this, earlier also we had a similar expression here, and I had said that h nu square variation is very small in the range of interest. In the range of interest was the bandwidth of the amplifier, which was only 10 to the power of 13 hertz, and therefore, that is a small fraction of light frequency. But when we measure the absorption spectrum, absorption takes place over a wide range, and therefore, now I would like to consider this also. If you remember, I had showed this as a variation because it is 1 by x square variation. So, this is h nu 1 over h nu whole square variation. Now, we want to plot it over a wide range. For example, from E g here to a wide range. Wide range, what do I mean by wide range? Is, let us say this is 1 electron volt, this is 2 eV. So, 1 eV, 2 eV, 3 eV. Earlier, where did we plot it? From Eg to Eg plus 0.1 eV or 0.2 eV, that is all, because that was the amplification band, and therefore, it was only a small fraction of this, and that is why I had assumed it to be constant. Now, I am not assuming it to be constant, because I want to see, for example, as we will see later, the absorption coefficient is important when you want to use the material for photo detection. So, a photo detector can detect over a wide range of wavelength, and therefore, we have to consider the absorption spectrum over a wide range of energies. The plot which I had made earlier, this amplification band corresponds to Eg to approximately Eg plus 0.1 eV or 0.2 eV. 0.2 eV is a very small range of this spectrum that I am going to plot now, and therefore, I had assumed this dependence as constant, but now we want to plot it over a wide range, and therefore, I have to consider that. The other part is, as you know, it starts from Eg, h nu minus Eg to the power half goes the same way, x to the power half dependence. So, this is h nu minus Eg to the power half. So, the net result is so the absorption coefficient. So, this is variation of alpha A. So, what I have plotted here is alpha A. Any question? Is it all right? Oh, I am sorry. I had showed that as 1, and this is Eg. It should. Thank you. Actually, it should start from Eg, because this is valid for Eg greater than h nu greater than Eg, and the density it starts from Eg. Yes, I am sorry. I wrote there 1 and okay. So, let the 1 be here. Does not matter, because there are materials with Eg less than 1. If you take germanium, it is 0.66 eV. So, from Eg, this starts from Eg. So, this is 1 eV here. Yeah, please correct it, that it starts from Eg, goes up, and then has a variation like this. This is what we expect to get in a semiconductor, the absorption spectrum of a semiconductor. But in practice, if you see the absorption spectrum, I will draw typical absorption spectrum just by the side here. So, let me again put 1 eV, 2 eV, so this is h nu, photon energy versus gallium arsenide. Let us start with gallium arsenide. All right, let us start with the lowest one. So, germanium is 0.66 eV, 0.66 eV. This is germanium. Let me plot typical numbers here. So, this is 10 to the power 1, 10 to the power 2, 10 to the power 3, 10 to the power 4, power 5 alpha in centimeter inverse. Centimeter inverse, alpha centimeter inverse. You can see gamma or alpha has to have inverse length dependence to centimeter inverse. This number is typical of gallium arsenide that I have plotted. So, typical numbers are 10 to the power of 2, 10 power 3, 10 power 4, 10 power 5 and so on. So, if I start with germanium, this has a behavior this is for germanium. It starts with Eg and it goes like this. We will see, we will discuss why it is behaving like this. If you take silicon, the next one, that is 1.1 eV. So, you know that silicon has a band gap of 1.1 eV and this does this. So, this is for silicon. The numbers and these are typical. It's all right, so little bit variation. So, next comes gallium arsenide. So, I have to gallium arsenide. So, gallium arsenide is here 1.42. So, 1.42. So, gallium arsenide does this. You see the difference. I am just for differentiation. This is what I have plotted for gallium arsenide. The numbers are very typical. If you see in a literature, you will see that the numbers are typical. Gallium arsenide. 2.16 gallium phosphide. Again gallium phosphide does this. So, this is gallium phosphide. Let me plot this and then we have something to discuss. Gallium phosphide. If you take gallium nitride, wide band gap semiconductor 3.3 eV, here it is also a direct band gap material and this goes like this. I am showing by a mark here, this is gallium nitride. These are direct band gap. Let me draw one more. This one here is indium phosphide, whose band gap is 1.35 eV. We have something to discuss. 1.35 eV. But if you just look at the graph, you can, all the ones which are dash marked here are direct band gap materials and the other ones are indirect band gap materials. So, just looking at the absorption spectrum, you can see something that for direct band gap materials, the absorption curve shoots up as soon as you cross the Eg. As soon as you cross the Eg, it simply shoots up almost vertically. Whereas, for indirect band gap materials, it goes like this. But for none of these, it appears that none of them seem to be coming down. Here we expect it to come down, but it does not seem to come down. There are several explanations that are due. This graph that we have obtained by considering a direct band gap semiconductor. We have considered a direct band gap semiconductor and we have concentrated only on the parabolic approximation close to the band edge. This is close to the band edge, but these bands do have behaviors which are very different. Close to the band edge, if you are seeing, let us say Eg plus 0.2 eV, 0.1 eV, 0.2 eV, parabolic approximation is a very good approximation, and based on that we have derived these expressions for a direct band gap semiconductor. But beyond that, this is not true. So, these curves are only valid close to the band edge, point number 1. Second, there is always, almost all materials also have an indirect band gap, and therefore, if you consider the theory of an indirect band gap semiconductor and find out the absorption, phonon assisted absorption, then you have a variation which looks like this, alpha indirect. So, this alpha that we have is alpha direct band gap. Alpha indirect, we are not going to this derivation, is approximately, empirically this is given that approximately you can show that this variation is of the form k0 some constant plus k1 of t into e to the power into h nu minus Eg whole square. We are not going to derive this. There is a, these are constants k0 and k1. K1 is a temperature dependent constant, h nu minus Eg whole square. So, this variation looks like this. Typically, what I am plotting is the variation at different temperatures T1, T2 which is greater than T1 and T3 which is greater than T2. That is because of this term K1 of T. The second constant K1 is a function of temperature. The numbers here are slightly smaller. So, 10 power 1, 10 power 2, 10 power 3, 10 power 4. So, they are little smaller. You can see these have already reached 10 power 4, 10 power 4. The direct gap has come to 10 power 4. This particular graph is approximately calculated for gallium arsenide. So, it should have been 1.42 eV, because if you use the parameters of gallium arsenide, then approximately 10 power 4 is the peak. Therefore, the net absorption is this plus this, absorption due to direct and absorption due to indirect. Plus there are other components, but this plus this will give you reasonably it explains this why gallium arsenide beyond this continues like this, because if you add this and this, you will get a variation which is approximately like this. So, that is why this portion is going up, both for germanium, gallium arsenide, almost all of them. This is the first reason why this is not coming down. Second, why in indirect band gap it goes like this, whereas in direct band gap it shoots up like this. Let us see the EK diagram. As soon as h nu reaches Eg, so this gap is Eg, it gets density of states for interaction. Rho nu, if you recall, the density of state, rho nu, okay, let me plot it here. So, rho nu versus E, we have already plotted this, then we have seen that it starts from Eg and goes up. So, as soon as photons reach this energy, there are plenty of states which are available and absorption starts immediately. Before this there is no absorption, and therefore, absorption is literally 0. There are other components, we will come to that, but right now absorption shoots up like this. That is why absorption shoots up in direct band gap semiconductors. What about indirect band gap semiconductors? So, if I want to plot the EK diagram of an indirect band gap semiconductor, an indirect band gap semiconductor, please see that this is Eg, so this gap is Eg. There are, as soon as you cross, there are states, yes, available states, Eg, but they don't any absorption going at an angle like this in the E diagram, in the energy space, is an oblique transition, violates the law of conservation of momentum. And therefore, although the states, in this case, the moment the energy exceeds Eg, all absorptions can take place, because all are vertical transitions which are highly allowed transitions. So, the probability of this transition is very high in the case of a direct band gap semiconductor, whereas in the case of an indirect band gap semiconductor, the probability is low because of this phonon assisted transition, because of violation of conservation of momentum, and therefore, the graph slowly starts increasing. Absorption can take place, but it increases relatively less rapidly as compared to direct band gap semiconductors. However, as the energy increases, please see, if I have a slightly higher energy, then this may make a less oblique transition. If I have more higher energy, this will make almost vertical transitions. If I, as h nu increases, as the frequency, as the energy of the photon increases, it can make vertical transitions, and that probability is very high. That is why you see germanium afterwards, again it does this rapid increase, because now vertical transitions can also take place. You have higher energy, band gap is the minimum energy. So, if you have photons incident with higher energy, they can cause vertical transitions which are highly probable, and therefore, the absorption coefficient shoots up. Same here with silicon. You see, it was going like this, then again it started increasing. Same here with gallium phosphide. So, it is as the energy increases, the probability of vertical transitions increase, and once of course the carrier comes here, then it will thermalize and it will come down here like this. This is thermalization, which we have discussed due to phonon transitions, and therefore, the graph again shoots up. So, two things, just by looking at the absorption spectrum, almost you can make out whether the material is direct band gap or indirect band gap. You just measure the absorption spectrum and you can make out whether it is a direct band gap or indirect band gap. Right at the beginning when we started with direct and indirect, how would one know which is direct band gap and which is indirect band gap? If you are given a piece of semiconductor, how would you know? Now, here is a simple test. So, you have an energy source. So, here is the semiconductor. Let us say you have a tunable source here, that is nu, tunable source which is frequency variable, and you pass light through this. This is light, I am talking of light, it is not electrical current, tunable source, and you measure the absorption output as a function of the frequency and simply plot this. You can identify which is a direct band gap material and which is a indirect band gap material. So, this term here explains for the transition which is going up. There are many more effects. These are not the only effects. What we have discussed is interband transition, conduction band to valence band or valence band to conduction band. This is interband transition. There are also intraband transitions which are possible. What is intraband transition? And there are Phonon transitions which are possible, and there are excitonic resonances which are possible. So, the absorption comprises of several effects, not just direct band gap or vertical transitions. So, what we have discussed is one, interband transition. That is band to band, valence band to conduction band, interband or band to band transition. There is intraband transition within the band. These are generally low frequency or low energy transitions. If you look at the EK diagram, every time you see, this is the EK diagram which tells about all the physics which I mentioned in one of the first classes. An electron which is sitting here can make an upward transition to a position here. An electron which is here makes an upward transition to a higher vacant state within the band by absorption of photon. Of course, this will require phonon assistance because there is a change in momentum, but an electron can make an upward transition here by absorption of photon, and this is called intraband transition within the band. But the carrier which is here subsequently will thermalize and come down through phonon transitions. This is intraband transition. So, when photons of a broad spectrum of energy is incident, so if you are finding the energy spectrum, if you assume that the source has all these wavelengths, then some of the wavelengths, particularly here at the lower energy, will result in an electron gaining energy and going to a higher vacant position, and this becomes a hot electron. A higher kinetic energy electron is called a hot electron, but subsequently it will come down by thermalization. This is intraband transition. Same thing can happen with a hole. A hole, for example, a high energy photon lifts an electron from here to here, then it leaves a hole here. A high energy photon incident here can make a vertical transition. So, this electron goes here, there is a hole here, but hole here is a high energy state, and electrons which are sitting here will immediately come down to this. An electron from low energy can immediately come down there. So, what happens? Then the hole moves here. An electron comes to that vacant state, means the hole moves up. This is also within the band. So, intraband transitions or vice versa. A hole which is sitting here can absorb energy and go to this place. So, these are intraband transitions. Generally, the energy of intraband transitions are less than band gap transitions. A third type of transitions are phonon transitions. But we know that phonon energies are typically in the range 0.01 eV to 0.1 eV. Phonons can also absorb energy. Low energy photons can be directly absorbed by phonons, or low energy photons can directly generate phonons within the semiconductor. And therefore, the absorption of photon, low energy photon, to give rise to phonons will also have absorption somewhere in this region, particularly low energy region. And a fourth type of absorption which is also possible are excitonic absorptions, excitonic resonances. Excitonic resonances. So, some of you may not be knowing what is an exciton. Exciton here refers to an excited electron hole pair. Hole pair. What it means is excited electron hole pair. Let us see, this is only an introductory . I write the EK diagram, erase it, explain something and erase it. Again you need EK diagram. So many times you need to draw the EK diagram. This is our traditional band diagram. An electron which is sitting at the bottom here, or a hole which is sitting at the top of this band, are low energy states, very low energy state. Therefore, the K is almost 0, which means the kinetic energy is very close to 0, very small kinetic energy, because kinetic energy is h cross square. So, h cross square K square by 2m. And therefore, if K is close to 0, that means they are low kinetic energy carriers, close to the edge of the band. An electron sitting at this place can absorb a photon of energy which is just near to Eg and make an upward transition if there is a vacant state, if there is a vacant state. So, there is a hole which is positively charged and there is an electron which is negatively charged. So, there is a hole which is close to the edge of the band and there is an electron which is just gone up to this Eg. So, the negatively charged, positively charged hole and negatively charged build up Coulomb attraction. If they are close in space, this is energy axis, but if they are close in space physically, then they form a hydrogen atom like bond, like an hydrogen atom. They behave like an hydrogen atom which is held by Coulomb interaction between a positively charged nucleus and a negatively charged electron. So, if you see the semiconductor lattice, there may be large number of atoms which are sitting. Maybe in one of the atoms there is a hole here, low energy hole. There may be an electron somewhere here and they form there is a Coulombic attraction. In addition to all the bonds which you have, covalent bonds, there is a Coulombic attraction between them. So, the electron and hole are localized. So, this localized particle, it is not a particle, its localized entity is called an exciton. The localized entity is called exciton. The binding energy though between these is extremely small. Typically the binding energy of this binding energy is of the order of 10 MeV, 10 milli electron of the order, typically 8, 10, 12, 15. Binding energy of this exciton is very small. In a hydrogen atom, what is the binding energy of hydrogen atom? More than 10 eV, 10 eV, more than 10 eV is the binding energy of hydrogen. But this is not exactly like a hydrogen atom, but it behaves, they are weakly coupled. There is some positive charge there or positive field and there is a negative field which tries to hold together with a very small binding energy, and this is called exciton. Normally at room temperature you do not see excitons in semiconductors, because the room temperature kinetic energy, average kinetic energy is 0.025 eV, which is 25 MeV. So, binding energy, that is kinetic energy, that is kT, is of the order of 0.025 eV or 25 MeV. So, this much average thermal energy is present in the material, and therefore, the exciton gets dissociated, because the binding energy is only 10 MeV. So, if already so much energy is present, the exciton is dissociated. Dissociated means they are no more holding together. So, they are free carriers. So, they behave like free carriers. So, at room temperature you would not see this, but due to this binding, due to this positive potential, the energy of this is slightly lowered. Energy of this pair is slightly lowered than Eg. This was at Eg, but the net state here exciton has a slightly lower energy, and therefore, this leads to states which are here close to the band edge, but little less than band edge. So, photons of energy slightly less than Eg can also be absorbed, and these are exciton states. So, there is a density of states due to excitons. So, photons close to the band edge, even a little less than actual Eg, can also get absorbed by in the formation of excitons. This is excitonic transition, and therefore, now we have, if I take the total spectrum, let us look at a total spectrum. We will discuss a little bit more about excitons a little later, because we are going to discuss the quantum confined Stark effect, and I will discuss about this probably in a later class. But if you now see the total spectrum H nu, we are starting now from 0.01, not 0.1, not so 0.01 eV, and let us say 0.1 eV, 1 eV, and then 10 eV. Anyhow, 10 eV is too much, we do not need. So, the whole absorption spectrum, earlier I had plotted 1, 2, 3, 4, but now we are looking at the entire absorption spectrum alpha of a semiconductor. Typical, I will plot this for a typical gallium arsenide numbers. So, you have 10 to the power of 2, 10 power 4. So, this is 10 to the power 1, 10 power 2, 10 power 3, 10 power 4, 10 power 5 centimeter inverse. All the interband transitions which we discussed were from here 1.42. Let us say this was Eg for gallium arsenide, Eg 1.42. is here. Now, I want to plot how it would look qualitatively, that there is absorption taking place at lower photon energies. So, this goes of course shooting up like this. I have overshot. Around 10 power 4 it will start turning. Okay. Below band gap there are some excitonic resonances. These are normally peaks like this, not below 1 eV here. So, excitonic resonances, and then there are free carrier absorption which looks something like this. Just showing you the overall, this is free carrier absorption, and then there are phonon absorptions. So, this part here is primarily due to free carrier. Free carrier, you remember, within the band, intraband transition. So, this was free carrier portion. This is excitonic resonances just below the band gap, excitonic, and then this is due to phonons, because the energy range here corresponds to that of phonons, that is creating vibrations in the lattice. So, energy is spent in creating lattice vibrations directly. So, this shows the and this is due to interband. So, in this complete spectrum we see all the 4 points which I have written. So, interband, excitonic, free carrier and phonon transition. This is the spectrum of absorption spectrum of a typical semiconductor. What I have plotted is for gallium arsenide, of course. I hope we understand why the behavior of spectrum comes. Before we stop, I want to just talk one step here, and that is how would the absorption look like in a quantum well. We have an expression for loss coefficient alpha, which had alpha is equal to so many constants. There was rho of nu, the density of states. It is the density of states which gave, and then Fg of nu or F0 here, that is Fa, probability of absorption, F0, which is Fa minus Fe. Let me write it fully. So, this is Fa of nu minus Fe of nu. Some constants here, rho of nu and this. And this rho of nu is the one which gave us the term h nu minus Eg to the power half, the density of states. And recall that the density of states, the first time when we plotted E, and this was Ev. So, this is Ev, Ec, and then we saw that the density of states goes like this. Density of states variation. This is, from this we derived all the absorption coefficients, and then we got this absorption coefficient which doing this. Band to band transition. We are in photonics, we are interested in band to band transition because we are looking at photon energies which are normally in the visible or IR region. So, we do not, so most of the times we will focus on band to band transition. So, the absorption coefficient was like this, rho nu was varying like this. In a quantum well structure, we know that rho nu is a step function. So, it starts from somewhere here more than E g, and then it is constant up to a certain energy, and then it remains constant here. So, this was E c plus E q 1. So, E c plus E q 1, that is q equal to 1 state. The density of states was constant. We have some values for this here. Then when the energy reached E c plus E q 2, so E c plus E q 2, there was a second step varying like this and then continuing like this. So, this is for the bulk and this is for the quantum well. This is for the bulk and it is a step function. Same thing here. So, if I assume that m c equal to m v, then I will have a similar variation. What does this mean? This means that for all photon energies from this gap here E g up to this, the density of states is constant. Therefore, the absorption should remain constant. Density of states is constant, it is no more varying, this is variation, but here density of states is remaining constant. This is, I have also plotted here, oh this is not k, why did I plot k here? This is rho c and rho v. So, rho of E, let me write rho of E, c comma v. This is for c and this is for v, rho c comma v. For all energy from E g up to this, the density of states, number of available states is constant, and therefore, the absorption coefficient must also remain constant, because absorption remains this almost constant here, and then suddenly the density of states increases, and therefore, absorption coefficient should suddenly increase. And indeed, quantum well structures show an absorption coefficient variation which is like this. So, if I want to plot in the same graph, then this is E g, there is no absorption at E g, first absorption starts at E g plus E q 1. So, in the same graph if I want to plot, it shows absorption, and then the absorption remains constant, almost constant except for the 1 by h nu square dependence, almost constant till E g plus E q 2, g plus E q 2, and then the absorption again jumps vertically, almost vertically, and then it remains constant. A step like variation of absorption coefficient. And if you connect this to the last class, a step like variation in the gain coefficient as well, and therefore, it is the density of states which determines what is the absorption spectrum or gain spectrum of a semiconductor. That is why we spend so much time on density of states. So, you get a step like variation, and this has very important applications. So, we will discuss about this in one of the later classes, but remember that a quantum well structure will show step like absorption spectrum. We will stop here and continue in the next class.